Hello, welcome to the World Wellbeing Project's Hadoop tutorial. In the next few minutes, you will learn about Hadoop and the MapReduce framework. We will also walk you through a simple example of how we use Hadoop to process language data. Before getting into the specifics, let us first motivate our problem. Typically, relational databases such as MySQL are used to store and analyze data. Even on expensive servers, when dealing with a large volume of data, single queries can take a long time to execute. The solution to this is to break the task into smaller parts and run each of these smaller parts on separate machines in parallel. This is where Hadoop comes in. Hadoop is an Apache open source framework written in Java that allows distributed processing of large data sets across clusters of computers using simple programming models called MapReduce. The beauty of Hadoop is that it's designed to scale up from a single server to thousands of machines. Additionally, each machine offers local computation and storage. That is, Hadoop brings the computation to the data. Hadoop consists of four basic parts, first of which is the Hadoop Commons. This contains the necessary Java files and scripts required to start Hadoop, as well as source code and documentation. Next is the Hadoop Distributed File System, or HDFS. This is designed to be a highly fault-tolerant storage system and can be used on low-cost hardware. Hadoop Yarn is responsible for managing computing resources in clusters and scheduling applications. Yarn can dynamically allocate cluster storage and computational resources, as well as maintain scalability as clusters expand to thousands of nodes. Finally, we have Hadoop MapReduce. This algorithm divides the task into small parts and assigns those parts to many computers connected over the network. It also collects the results to form the final data set. We will explore this in more detail later. The Hadoop distributed file system uses a master-slave architecture. The master is a single node called the name node, which manages the file system data. One or more slaves or data nodes store the actual data. HDFS is designed to reliably store very large files across a large number of machines. It stores each file as a sequence of blocks, and each of these blocks is replicated for fault tolerance. Both block size and number of replications are configurable per file. The MapReduce algorithm consists of three stages: map, shuffle, and reduce. In the map step, a function is applied to the local data. Since all data is replicated, the name node ensures that all data is processed once. The output of a map step is a key value tuple. Next is the shuffle step. Here Hadoop combines the output of the map function based on the key. All values with the same key are combined and sent to the reduce step. With all the data grouped by a single key, the reduce step processes each group in parallel. The entire MapReduce algorithm can be thought of as two successive functions which act on key value pairs. The map function is applied to a key value pair and returns a new pair, often with a completely different data type than the input. Similarly, the reduce function acts on one of the key value map outputs and again returns a pair. Note that transforming your algorithm into a MapReduce algorithm is not always simple. Often straightforward algorithms can become quite cumbersome and need multiple MapReduce phases. With Hadoop, once this part is done, we can implement the same algorithm on a cluster with one node or a cluster with 1,000 nodes without changing our code. To get a better understanding of how the MapReduce framework works, we consider the task of filtering unwanted language features. Often, when dealing with large amounts of language data, we need a way of paring down our data set. One way of doing this is to remove very rare words. In this task, we want to identify all features used by at least some percentage of users or more, and then remove the rest. Usually, this percentage is low. For example, we often keep features used by 1% or more. Here's an example of a typical feature set in the form of 1-grams. In this set, we have 3 columns: user ID, feature, and value. The user ID corresponds to the author or source of the text. The feature column contains the actual language, which in this example is a single word or token. The final column is a numeric value of the feature, where we count the number of times the author used this word. We feed our mapper one line of the table at a time. It reads in each line and outputs a key and value to be acted on by the reducer. The feature is used as the output key, and the entire line, including the feature, is used as the value. When viewed as a function on key-value pairs, the mapper acts on a key and file line and then returns a new key and value. For example, we read in the line 1001 they 5 and return the key they and value 1001 they 5. Since the feature is used as the output key of the mapper, after the shuffle phase, each reducer gets a single key and all values corresponding to that key. Here we see the first reducer receiving all values with the key they. Similarly, the second reducer receives all values corresponding to the key hopefully. The third reducer receives all values with this sum key. And finally, the fourth reducer receives all values with the no key. Since the sum and no features are used by only one user each, we remove those features and output only those used by 2 or more users. As you can see, the entire program is composed of 2 main functions, map and reduce. At no point did we consider the number of mappers or reducers used, nor did we consider the hardware or cluster size. Once a program is written in the MapReduce format, Hadoop takes care of all computational resources. That wraps up our tutorial. Thank you for watching. Our Hadoop code, as well as various other datasets and lexica, are available to download at www.bp.org.